Hi, I'm Matt. Let's talk about classification models in machine learning and how we evaluate whether they are good or bad or what weaknesses they have. Now, there are a lot of metrics in machine learning, and in classification models, that's very true as well. But there's really one key thing that I look at when I'm trying to determine is this a good model or is this a bad model? And that's the confusion matrix. Okay? A confusion matrix looks, a little bit like this, and it's got these rows and columns. So here I've got a 2 by 2 grid where we're predicting a value of fraudulent or non-fraudulent. So think about this as maybe a insurance claim or something of that nature, right? Or a purchase. We're going to be classifying that purchase as potentially fraudulent or potentially non-fraudulent. Now, that's what our model is predicting. Now, that thing that we're classifying, it either is or it isn't, and that's where our rows come in. So this row here has cases where it is fraudulent, and this row here on the bottom has cases where it's not. Okay, so we like it when our model predicts the right value. So if something was fraudulent, our model might predict it was fraudulent, and that would be this box here. This would be our true positives. Now, if it's non-fraudulent, we're going to hope that our model is going to predict that it's non-fraudulent. Okay, that'd be a true negative. Now, notice that when our model gets it right, it's a true. On the other hand, when our model gets it wrong, well, that's a false, right? So false means we got it wrong, and true means we got it right. Now, the second word there is positive or negative, depending on if our model predicted yes or no. So in this case, this column here is all about we predicted no, and this column here is all about we predicted yes or positive. So we look at this and we see, all right, this model, 144 times it predicted a no and it actually was non-fraudulent. 16 times it predicted yes and it actually was fraudulent. And then, there were 10 cases where we predicted it was fraudulent and it actually wasn't, and 30 cases where it was fraudulent and we predicted it wasn't. So this is an okay model. It's not a perfect model by any means. We're going to explore many metrics associated with this, but we can get a good sense of how the model is performing just by this matrix. Now, a lot of the metrics that you're going to see associated with confusion matrices are kind of driven by this matrix here, right? It's like so we can look at any one of these these metrics and get a good sense for how our classification model is performing. So let's talk about all these different metrics and what we can get from how we can calculate them. The first one we want to talk about is accuracy. Now, accuracy is we're basically saying, hey, how much of this whole thing did I get right? What percentage of cases am I getting right? So in this case, there's actually 200. There's 200 things, and we're calculating the number of those that we got right. So we calculate that by the number correct divided by the total. Well, number correct in this case is 160, and there are 200 total data points here, and so that's going to math out to 80%, right? So 0.8, our accuracy is 80%. So not amazing, but not awful either. Okay, so this is just one metric we have. And accuracy, it tells a portion of the story, but it doesn't tell the whole portion. So let's look at some more. Recall is basically our model's ability to recognize a value that we should be predicting true to, right? So in a case where it is fraudulent, what percentage of the time are we flagging it as fraudulent? So I think about recall as recognizing true values. So that R and recognizing, that's my mnemonic, right? We calculate this by taking the true positives, that's this box right here, and dividing it by the total number of things in this first row, right? So what percentage are we getting right? In this case, 16 divided by 36, it's not a great number. This is only 44% of the time. So our model is actually, it only recognizes fraud 44% of the time. So that's a significant flaw, even though the model has 80% accuracy. Now, if we would look at the no row here, specificity. This is how much can we trust? If it is no, how much what percentage of the time are we actually predicting no? And we get this by calculating this 144 divided by the total number in this whole row here. So that's where we take our true negatives and then sum everything else up. And in this case, it's 144 divided by 154. So we actually have a specificity of 93.5%. So pretty reliable at recognizing the no's. This is the model's key strength. Okay, so let's looking at our rows. We have some metrics associated with the columns, as you would expect. If we're looking at the yeses, we have something called precision, or a positive predictive value. You'll hear it called sometimes. But precision here is basically If we predict yes, what's the percentage of the time that we're right? Okay? So we calculate this by taking the true positives and dividing it by the total number of items in this column. So in this case, it's going to be 16 divided by 26, or 61.5%. So if we're predicting yes, we're likely to be reliable, but it's not a very strong percentage. So this helps us understand our model's strengths and weaknesses. Now, on the other side of this, there's the negative predictive value, which is basically how reliable are our no's. If we're predicting no, what's the chance that we're right about that? We get this by taking this true negatives here and dividing it by the total in this column. In this case, that's 144 divided by 174, which is going to give us 82.8%. So, pretty decent negative predictive value. This model is very good at predicting these true negatives here. That's maybe the key strength of the model. Now, we can kind of combine some of these rows and column metrics to form something we call the F1 score. The F1 score, or sometimes you'll hear it called the harmonic mean, is where we basically take the precision and recall and we multiply them together and by 2, and then we divide all of that by the sum of the two together. This is kind of the mathematical way of sort of averaging out the precision and recall to kind of get a balanced score that's somewhere between them. So our precision is 61.5% and our recall is 44%. And so we kind of average that out by plugging in these numbers, simplifying it down, and then calculating that down. We have an F1 score of 0.513. So it's not an amazing F1 score. A perfect F1 score would be a 1, and a horrible F1 score would be a 0. But still, we can see there's a decent range of improvement that we could have in our model. So this can give us kind of a nice balance between the precision and recall metrics. And note that the F1 score is quite different than the accuracy of 0.8. Right? So accuracy is just one small portion of the pie, and in fact, it can often be deceiving. Now, there's another set of metrics we want to look at, and this is called the prevalence, and this tells us basically how our data is distributed. You might have noticed that we have a lot more negative cases, non-fraudulent cases in this case, than we have positive cases, right? So prevalence helps us understand the distribution of our data among these different classes. A class here would be if it's actually yes or if it's actually no. And so we basically calculate the prevalence as the count in the row divided by the total overall for the confusion matrix. So each row is going to have its own prevalence. So the prevalence of yes is going to be 46 divided by 200, and prevalence of no is going to be 154 divided by 200. Note they're both divided by the total amount. And we calculate this out, and we see that the prevalence of yes, in this case, is 23, and the prevalence of no is, 77. So there are a lot of metrics that we have associated with confusion matrices, but a confusion matrix can really give you a very quick glimpse into the performance of your model and helping you understand its strengths and its weaknesses. And many other metrics associated with classification models are really derived from these confusion matrices. So I hope this was helpful for you. If there's anything else you're interested in classification models or machine learning in general, let me know. I'd be happy to talk about it. But thanks for your attention, and I hope you enjoyed this.